The weapon entered service through an emergency requirement. The regular army had lost many anti-tank guns. The Home Guard received improvised alternatives instead. One such expedient device was the Smith gun. It was designed by retired Major William H. Smith. He worked with the engineering firm Trianco Limited. The intention was a cheap, transportable anti-tank piece. The gun used a smooth-bore 3-inch barrel. Barrel length was approximately 54 inches overall. The bore was optimized for modified mortar-type ammunition. The carriage resembled an oversized pram structure. 2 large steel wheels dominated the side profile. Between them sat a basic metal shield plate. The shield provided limited frontal splinter protection only. The total system weight exceeded 270 kilograms. This mass included wheels, axle, to cradle and shield. In travelling configuration, the weapon lay on its side. The muzzle projected forward, clamped to the limber. The limber carried ammunition and doubled as towing interface. Standard towing speeds were low to prevent wheel damage. The key feature was the tipping deployment method. On arrival, the crew manually rotated the gun. They tipped the entire carriage through 90 degrees. One wheel became a flat-base plate on ground. The opposite wheel then formed a partial overhead shield. The barrel now sat roughly horizontal between both wheels. The axis of rotation passed through the grounded wheel hub. This allowed full 360-degree traverse capability. Elevation range extended up to approximately 40 degrees. Depression was constrained by shield geometry and carriage clearance. So the deployment cycle introduced several ergonomic problems immediately. The weapon required firm, reasonably level ground for stability. Soft soils allowed the wheel plate to sink asymmetrically. Uneven ground produced unpredictable traverse resistance and tilt. Crew drills therefore included ground selection before tipping. Home Guard manuals stressed choosing hard standing if available. Urban pavements, roads and concrete hard standings were preferred. In rural positions, crews sometimes laid improvised timber pads. These were cut from packing crates or local fencing. Such measures reduced subsidence but slowed deployment time. The gun nominally used a 4-man operating crew. A typical drill allocated roles precisely for safety. Number 1 acted as layer and firing operator. Number 2 loaded and handled the ammunition supply. Number 3 supervised fuse setting and range confirmation. Number 4 managed tow arrangements and general security. In some Home Guard platoons, was crews operated under strength. 3-man detachments were common due to manpower limits. This increased individual workload during tipping and positioning. Fatigue became significant when moving the gun repeatedly. The ammunition family reused existing 3-inch mortar bombs. Bomb bodies were modified with suitable driving components. Anti-tank rounds relied on shaped charge-style warheads. Penetration performance reached approximately 60 mm homogeneous plate. This was adequate against early war medium armour types. Anti-personnel rounds carried high explosive fragmentation fillings. Fusing options included impact and graze-sensitive nose elements. Later batches incorporated safer fuse designs after early accidents. Nominal maximum range figures approached 800 meters. Effective ranges in field use were much shorter. The weapon operated at relatively low muzzle velocities. Trajectory was high, curved, and strongly affected by wind. Accurate fire demanded consistent range estimation and careful elevation. Training ammunition allocations were severely limited in practice. Many detachments received only 6 or 7 live rounds. This represented the entire wartime stock for some platoons. Consequently, layers rarely developed intuitive feel for trajectory. Range tables existed but were based on controlled trials. Actual field deployment conditions deviated from test assumptions frequently. This discrepancy contributed to doubts about achievable accuracy. The manufacture followed a mixture of commercial and ordnance standards. Trianco and subcontractors handled carriage and wheel fabrication. Barrels and breech components used established gun steel alloys. Wheels were pressed and welded from heavy gauge rolled plate. The shield panel was cut from standard armour quality sheet. Axle assemblies used machined forgings with plain-bearing bushes. Production runs began late 1941 under urgency. Quality control varied across batches due to dispersed subcontractors. Inspection reports mention inconsistent wheel tolerances and alignment. Misalignment increased rolling resistance and complicated tipping maneuvers. The tipping concept demanded robust wheel and hub construction. Impact loads during rotation were transmitted through a single wheel. Designers thickened the plate and added reinforcing ribs locally. However, repeated field tipping caused gradual deformation over time. Bent rims produced wobble and uneven base contact during firing. This deformation translated into variable recoil absorption characteristics. On poor surfaces, the gun could shift under discharge. To counter this, crews sometimes chocked the grounded wheel. They used bricks, stones, or prepared timber blocks beneath edges. These unapproved methods reduced movement but slowed readiness transitions. The breech incorporated a simple sliding block arrangement. Ignition employed conventional percussion primers in cartridge cases. Propelling charges were loaded in increments behind each bomb. Charge weights varied with desired range and target type. An incorrect charge selection risked overstressing the smoothbore barrel. Operation manuals specified maximum permissible charge combinations clearly. Nevertheless, documentation assumed literate, technically confident part-time crews. Many Home Guard units included older men with limited engineering background. Instructors therefore simplified lessons, emphasizing safe standard charges. This approach preserved safety but limited tactical flexibility significantly. The organizational context further complicated deployment and training. Home Guard responsibilities were primarily local static defense duties. Smith guns often guarded roadblocks, bridges, and airfield perimeters. Some regular Army and RAF Regiment detachments also received them. However, invasion did not materialize during their service life. As a result, the weapon saw only exercise use. Perceptions of safety were therefore shaped mainly by training accidents. Positive combat validation never balanced the record of malfunctions. This asymmetry heavily influenced reputational assessments by commanding officers. Some units subsequently restricted or withdrew the gun from roles. The first major accident occurred during a live-fire exercise. A round detonated prematurely while still within the barrel. The explosion killed Corporal Cecil Edward Maynard instantly. He served with an RAF Regiment squadron at that time. Subsequent inquiries examined fuse sensitivity and handling procedures. Investigators considered the possibility of incorrect fuse setting practices. They also examined manufacturing records for that ammunition batch. Their reports highlighted inconsistent fuse assembly torque and sealing quality. Recommendations led to modified fuse designs and tighter inspection. Despite changes, the psychological effect on users remained substantial. RAF Regiment authorities soon reassessed these weapons' suitability. Their units often trained on airfields with limited cover. Explosive accidents in such environments were considered unacceptable risks. In 1943, the regiment withdrew remaining Smith guns. Withdrawal orders cited safety concerns and alternative weapons availability. Other units retained the guns, but tightened training regulations considerably. Live firing days became rare and highly controlled events. Ammunition allotments shrank further as war priorities shifted. Many crews completed entire service without firing live rounds. Their familiarity came mainly from dry drills with inert bombs. Transport aspects formed a central part of the design rationale. The gun and limber combination could attach to civilian vehicles. Planners expected Home Guard detachments to use local transport resources. Small cars, vans and light trucks were typical towing platforms. Regulations limited towing speed to protect wheels and axles. Some units ignored this and attempted higher speed road moves. Such practices accelerated tyre and bearing wear significantly. Ordnance inspectors recorded cracked spokes and overheating hubs. These defects reduced reliability when rapid deployment was actually required. Later circulars formally prohibited extended towing except in emergency. The gun could also be manhandled short distances by crew. The toggle ropes were issued to assist movement over difficult ground. Each rope clipped to frame attachment points at designated locations. Crews hauled from the front while one man steered. On slopes, movement demanded careful coordination to prevent uncontrolled rolling. Training pamphlets advised positioning additional men as side restraints. However, part-time volunteers often lacked regular physical conditioning. Extended maneuvering of the heavy carriage produced rapid fatigue. Fatigued crews were more prone to procedural mistakes under stress. Several tipping mishaps occurred when men lost grip suddenly. Ergonomic assessment shows multiple awkward working positions for crew. In firing configuration, the barrel sat low above ground level. The layer often knelt or crouched awkwardly behind the shield. That recoil movement transmitted through the wheel could jolt his stance. The loader worked to one side within a confined space. He had to lift bombs around the wheel rim structure. This motion intersected with the traverse arc of the gun. Clear verbal coordination was therefore essential during laying and loading. In low-light conditions, spatial awareness degraded and collisions increased. Bruising and minor injuries recorded reflect this cramped arrangement consistently. Fuse setting required precise manual actions with small components. Operators used simple key tools and graduated scales on fuse bodies. Cold weather and gloves reduced tactile feedback during adjustments. Instructors sometimes authorized bare-hand operation for better control. This increased vulnerability to cuts from metal edges and fragments. Reports mention minor blood contamination on some training fuse stocks. Such details illustrate the absence of modern ergonomic design standards. The system prioritized improvisation over long-term human factors optimization. Home Guard authorities accepted these trade-offs during invasion scare conditions. Later, with reduced invasion risk, acceptance levels altered significantly. Ballistic performance against armour remains difficult to validate empirically. Trials reported penetration of medium plate at limited distances. Results depended heavily on impact angle and standoff range. Shaped charge warheads required controlled orientation on target surface. High trajectory firing complicated achieving ideal strike geometry consistently. Field conditions introduced concealment requirements and obstacles near targets. Her gun crews had to balance cover with effective engagement geometry. Static roadblock positions sometimes forced suboptimal firing angles. Commanders therefore recommended ambush tactics at very short ranges. This increased probability of hit but also crew exposure time. Within the broader Home Guard arsenal, several alternatives existed. The Northover projector and Blacker bombard offered different compromises. Both systems also emerged from emergency anti-tank requirements. However, they avoided the tipping wheel-based concept entirely. They used simpler mounts with more conventional crew postures. Comparative commentary often criticized the Smith gun's mechanical complexity, yet some officers valued its theoretical 360-degree traverse advantage. In practice, terrain and obstacles reduced that advantage in many positions. Rotating fully around the wheel required clearance and careful cable routing. Telephone lines, toggle ropes, and vegetation often impeded continuous traverse. Production figures reached approximately 3,000 to 4,000 guns total. Issue priority went to areas considered vulnerable to armoured thrusts. Coastal counties, key junctions, and airfields received early allocations. Ammunition deliveries lagged behind gun distribution across the network. Logistics branches struggled with fuse updates and storage requirements. Dangerous early fuses required segregation from later safer batches. Storehouses maintained separate racks with clear signage and paperwork. Home Guard quartermasters handled this additional complexity alongside routine duties. Mislabeled crates occasionally reached units during busy periods. Such errors further reinforced doubts about the system's reliability. The bureaucracy around the weapon evolved as experience accumulated. Initial instructions adopted optimistic language about power and accuracy. Later amendments added extensive cautionary notes on safety procedures. Circulars introduced additional checks before live firing authorization. Commanding officers had to certify crew competency in writing. Medical officers sometimes provided input based on previous accident reports. This layered approval process slowed opportunities for realistic practice firing. As the war progressed, higher command attention shifted elsewhere. Newer, more conventional anti-tank guns then entered regular army stocks. Home Guard units also received other simpler weapons for close defense. The Smith gun therefore occupied an increasingly marginal operational niche. From an engineering perspective, the central innovation remained mobility. The gun leveraged large diameter wheels for low rolling resistance. The same wheels formed a broad base when tipped sideways. This avoided separate heavy base plates or complex outriggers entirely. Weight savings translated into more manageable towing by light vehicles. The concept reduced manufacturing of additional stabilizing hardware components. However, combining mobility and platform structures created conflicting requirements. Wheel rims had to survive both rolling and impact loading. Tyre materials needed to perform as both tyres and pads. Meeting both demands perfectly exceeded realistic wartime engineering resources. The base wheel's contact patch defined stability during recoil events. On hard surfaces, friction coefficients remained predictable and constant. On grass, gravel or mud, friction varied rapidly under stress. Recoil vectors could generate lateral slip around the wheel circumference. This movement altered barrel direction between successive shots subtly. Instruments for precise bearing measurement were rarely available at platoon level. Crews therefore relied on visual references to correct between rounds. Use of nearby buildings or tree lines assisted with orientation. Nevertheless, fine directional control never matched conventional split-trail guns. The weapon therefore remained a short-range, opportunistic system effectively. Maintenance routines attempted to mitigate some mechanical vulnerabilities, so weekly inspections included checking wheel fixings and hub lubrication. Grease nipples were accessible through small apertures in wheel discs. Barrel bores required regular cleaning to remove combustion deposits. Infrequent firing meant corrosion posed a greater threat than erosion. Units stored guns in sheds, garages, or improvised shelters locally. Humidity and condensation affected metals differently in such conditions. Some detachments applied unofficial paint schemes for extra corrosion resistance. These modifications sometimes interfered with moving parts or tolerances. Ordnance officers occasionally ordered removal of non-standard coatings. The training curriculum split into classroom and field components. Classroom sessions covered basic principles of anti-tank engagement. Instructors explained armour thickness, angle of impact and penetration. Students studied silhouette recognition charts for common enemy vehicles. These materials assumed possible encounters with German tanks and armoured cars. Field sessions then translated principles into emplacement and aiming drills. Each crew rehearsed deployment from road movement to firing state. Time standards were recorded for internal assessment and improvement. Tipping the guns safely formed a discrete time drill sequence. Any uncontrolled tipping or miscommunication resulted in recorded training deficiencies. Paperwork associated with each gun followed standard ordnance patterns. Every weapon carried a serial number stamped on key components. Associated logbooks listed inspections, repairs, and ammunition expenditures. Accidents, however minor, required detailed entries and formal statements. The commanders signed off each live firing event after reviewing results. At higher echelons, aggregated data informed policy reconsiderations. Patterns of minor injuries and mechanical issues became visible over time. The Smith gun gradually appeared as a high administration burden. Alternative weapons with simpler drills generated fewer reportable incidents overall. This bureaucratic reality weighed against continued wide-scale deployment. Some technical reports praised specific aspects of the design concept. They noted the advantage of all-round traverse from one footprint. Engineers also appreciated the efficient reuse of mortar ammunition stocks. Smoothbore construction simplified manufacturing relative to rifled tubes. The carriage offered reasonable frontal protection relative to weight class, as the shield could stop small arms and fragment threats from ahead. In static roadblock scenarios, these characteristics held practical value. However, real-world road geometry often constrained firing arcs sharply. Buildings, walls, and street furniture limited rotation beyond narrow sectors. Thus, theoretical all-round coverage rarely materialized in built environments. The fire control method remained basic compared with regular artillery. Simple open sights assisted with directional alignment on visible targets. There was no dedicated rangefinder integrated into the system. Range estimation relied on observer judgment and limited range cards. Where available, external observers used binoculars or simple periscopes. Communications between observer and gun often used shouted commands. In noisy exercises, though this channel degraded due to background interference. Telephones or field telegraph systems were rarely installed for home guard. Consequently, coordinated targeting across multiple guns proved difficult operationally. The system was best suited to single-gun, point defense scenarios. When war ended, formal obsolescence followed quickly for the Smith gun. By 1945, threat patterns had changed decisively. Standardized, safer weapons dominated post-war defense planning discussions. Surplus Smith guns entered storage, disposal or museum collections gradually. Curators later highlighted the gun as an example of improvisation. They also emphasized the associated engineering compromises and safety issues. Modern assessments treat it as a case study in emergency design. The weapon illustrates tensions between ingenuity and ergonomic practicality. It also demonstrates how bureaucracy responds to technical risk over time. User experience, accident records, and logistics pressures all shaped final judgment. Today, preserved examples show the physical reality of the tipping concept. Visitors can observe wheel construction, shield arrangement, and crew space. Measurements confirm the low profile and constrained working volumes. Traces of wear on wheel rims evidence repeated tipping cycles. Such artifacts corroborate written reports of handling difficulties and deformation. For researchers, the Smith gun provides a tangible archive of constraints. Limited materials, urgent timelines, and evolving threats all influence decisions. In that environment, safety margins were narrower than peacetime norms. Then the resulting system functioned, but with elevated operational risk profile. Commanders eventually accepted that this profile outweighed its practical advantages.